Okay, here's where we were last time. Okay, time to get started. I need to get going here. I need everybody to settle down so we can get going here. So here's what we were talking about last time. We were talking about so we were talking about Green's theorem last time. Remember, the idea of Green's theorem is that we have an accumulating quantity that we do with as we do with accumulating quantities. Namely, we argue that the whole is the sum of the parts, right? And then secondly, we argue that, look, on each little piece, I can compute this quantity as if it's a kind of a stuff, namely stuff per unit size times size, in this case area. Right? So you can do this kind of an argument with any sort of an accumulating quantity, and we established last time that circulation, weirdly, unexpectedly, circulation is an accumulating quantity, and so you can do this argument right here. And so the punchline, again, is our theorem that boundary circulations can be computed with a double integral over the interior of the curl operator. Okay. All right. And then reminder, and just be explicit about it, curl, right? That's one of several different names and notations, etc., that you might encounter this idea of what deep down fundamentally, my cornerstone point of view on this, the way I always think about curl, right here, it's circulation density. Notation is just notation. Formula is just a formula, right? But what is it? Cornerstone fundamentally, it's circulation density. It's how much of this accumulating quantity called circulation is there per unit area in wherever you're looking. So that's the big idea. And of course, we talked about these other names and notations that you might encounter here or there. Okay, so that's what we did last time, and we had a couple of examples we saw, and now we're going to see a cool application. Oh, yeah, did you?
Yeah, just a question.
Okay.
Because you said that curl is just circulation density.
Yep.
Is that why we need it to be scalar and not like the one?
It's kinda.
Okay.
Yeah. I'm going to say it works out. It's not that we need it to be a scalar. It's that it is a scalar in this case.
Mm-hmm.
And when we do a three-dimensional version of this, it will turn out to be a vector, as it turns out. But that's a very different scenario. There's a lot to say to build up to that.
But
Yeah.
would it still be circulation density even in the vector case?
We'll cross that bridge when we get to it. Yeah. There's a lot going on with that I can't quite preview right now. Yeah. Okay, so we did a bunch of examples. On to a new application. This is a very clever idea. It has narrow application. But if you find yourself in this circumstance, it's really cool. So what you're going to notice is that right here, in fact, is just Green's theorem. We have a boundary circulation on the left. We have a double integral of curl on the right. It's just that Green's theorem has been applied to this specific vector field 0, x. Now, why on earth would I choose to look specifically at this one vector field? And turns out this vector field has a lovely property, very valuable property, and that is its curl is 1. Now, so... right? Everything's got a curl. It's got to be something. What's so great about curl being 1? What's nice about that is that means that this integral literally tells you the area, right? So altogether then what we have is a theorem that says if you want to compute the area of some two-dimensional region, you can just, this is very strange, but we can compute a boundary circulation and that will compute the area for us. Very weird. The one little asterisk on this is the notation. Now, what I have circled here, these are the same thing, written two different notations. It's exactly the same thing. Remember, we have this idea, if you have a vector line integral, you can write dx in coordinates. You can explicitly write out that dot product. And this, in particular, in coordinate notation, looks like what I have on the left here. And this is one of these instances, and this happens sometimes, where I got to hand it to the coordinate notation here. I think it's a little bit more compact. a little bit more convenient. So in this case, more often than not, you'll see the theorem written like this. Okay. Now, who cares? What does this do for us? It turns out that there is a special, let's see how to say this. Depending on what the domain is, this integral can be easy to compute. Integral x dy. Specifically, if you're only looking on a line segment. Just a line segment. Now to be clear, that's not what this is, right? This is an integral around a boundary. A line segment can't be a boundary, right? So what am I supposed to do with this if what I need is an entire boundary? Well, I can consider a lot of scenarios where the boundary in question is made up of a bunch of line segments. Right? And what I can do then is use this formula, and I'll go talk about the details in a second, to compute one edge at a time. Right? And then I just have to add up over kind of, if you will, all of the various line segments that make up the boundary. Just add them all up, and you can get a total. Right? So if you are talking about a polygon, even a creepy, weird polygon like this one, right? You want to compute the area inside of there, and by the way, none of these angles are right angles, if I remember correctly, or at least at a minimum, most of them are not right angles. This would be a horrendous calculation if you were to break this up into little triangles, right? No fun. But it turns out to be easy arithmetic if you use this little fact here. So what I've left as an exercise for y'all, this is a good, healthy exercise, is show that on a line segment, just a line segment, green. If you're looking just at a line segment, integral x dy on that line segment is computed by this very compact and convenient formula. It's just the average value of x times the change in y. And so, for example, if I were to look again on this first edge here, and let's presume that the coordinates of the endpoints are sort of as indicated. The average value of x between 1 and 12 is 6.5. The change in y on this edge, and do keep in mind the direction, right? The direction matters. On this edge, we're going up and to the right. And so as I traverse that edge, y increases by 5, from 1 to 6. And so on that piece, the line integral on that piece is just, x bar times delta y, which is 65 halves. And now repeat for the remaining line segments, and I've got the arithmetic here. You can check the arithmetic if you like. But we computed then the total area here, this wacky thing, whatever that is, that area is 19. So, kind of a neat application. Comes up sometimes. Okay. All right, so next thing, flux through a curve. Now, y'all hopefully remember flux in 3 dimensions. Back in Chapter 3, we talked about if you have a surface, in particular a flat piece of area, and if you have a fluid that's kind of moving through space, including moving through your flat piece of area, flux says how much fluid per unit time. Volume or mass or quantity in whatever sense, depending on how you set up your vector field. How much fluid per unit time is passing through your surface. So here we're going to consider a 2-dimensional version of that. And here the fluid, of course, isn't going to pass through a surface. This is all 2-dimensional. There are no surfaces inside of 2 dimensions. There are curves, right? Curve would be the analogous thing that you might want to consider how the fluid passes through. And so it turns out our formula is length times and then the dot product of the vector field with your orientation vector. And of course, we do need, if you're going to talk about, fluid passing through a piece of curve, well, which direction? Is this the positive direction, or is that the positive direction? You need some indication of which way you mean. And a normal vector pointing in the direction that we want to call the positive direction is how we indicate that. Okay, so this formula, why does this formula work to compute that flux? I think is a nice exercise. Good news, it's just like what we did back in Chapter 3. It's the same thing. It's just two-dimensional instead of three-dimensional. So I think this makes this a really nice exercise to think about how would you adapt, and by the way, borrow liberally, shamelessly from what we did back in Chapter 3. Same basic idea, just adapt it appropriately, and you'll get this as your final answer. So again, nice exercise, give that a shot. If you get stuck, come on into office hours. I'll be very happy to help, show you how, whatever you might get stuck on, or help you get started, whatever you might need. Okay, but here in class, we're just going to sort of work with this as a given. All righty. On the next page, I'm going to first, I'm going to keep your attention off of this stuff just for a moment. And off of this just for a moment. We'll come back to it, but for the moment I don't want that to be a distraction. We're going to talk about a closely related idea called boundary flux. And the big idea is if you have some region, and as I often do, there's a large region here, and I'm just looking at part of the sort of the boundary of this large region just so we can be focused in. There is an entire, the boundary goes all the way around. I just want to just draw this one part of it here. The boundary, something like that. And I hope y'all all had the same knee-jerk reaction as soon as I said the word boundary. Your ears should perk up and think, orientation. Which way is the orientation? What does the orientation mean? Right? Remember, in chapter 6 and 7, the word boundary is an oriented thing. And the orientations are all according to certain conventions, which are kind of arbitrary, but they're all standard and they all fit together in important ways. And so arbitrary, yes, but being as they are standard, it's not optional, right? We have to get on board with all of the accepted norms. So here is the norm. When you're talking about flux, boundaries are oriented outward in the sense of away from where the region is and into where the region isn't. So this is the standard convention for what we mean by boundary orientation through the boundary. Okay, so how would I compute the flux through the entire boundary? Well, okay, problem. You look up to here, what do we know about computing flux? Well, I only know how to do it if I have a straight line segment. And I also only know how to do it if my vector field is constant. That's all this is good for right here. Constant vector field, straight piece of curve. And that's not what I have here, but what I can do is say, look, if I were to break up my curve into a bunch of little itty-bitty pieces of curve, such as this, on any individual little piece of curve, I can talk about how much flux is happening on that one little piece. And then I can add up over the whole. We'll worry about that part later. Let's just think about here, how will I compute on that little piece? Well, on that little piece, check it out. It's a little piece of curve, and so it's approximately straight. And it's itty-bitty, so the vector field's approximately constant. Right? On little bitty things, we get to make nice little assumptions and sort of assume things are flat and constant and nice. which is totally awesome. And so on that piece, we use this formula right here. F dot n times the length of that little piece of curve. So on that piece, F dot n, and of course the length of this little piece of curve here is ds. Everybody all right with that so far? Now we're in trouble at this point because this integral here is not something we're previously familiar with. We've never computed integrals of this sort before. F dot t ds we have, but not F dot n ds. And we're staring down the barrel of F dot n ds. So it's not clear exactly how we're going to do this. And here's where I'm going to make this clever argument up here. Let's bring all this back up on board. I find myself looking at F dot n. There's F, there's n. Here's the slick move. Very clever. I wish I'd thought of this. We're going to take that whole thing and rotate 90 degrees. And if you rotate F and N both by 90 degrees, the result, N will rotate into the unit tangent vector. Now, geometric appeal, if you have a unit vector perpendicular, rotating 90 degrees makes it a unit vector tangent to the curve. That's what T is. And notice it's even pointing in the correct direction because the region's on my left as I go in the direction of that T. Right? Very nice. And then if I rotate P comma Q, well, now this is just an old linear algebra thing, but again, you know, Math219, linear transformations, matrices, columns are the images of the standard basis vectors. Again, make sure you can do that, but 90 degree rotation applied to P comma Q gives me minus Q comma P. So if you're good with that, cool. If you're not, come on into office hours. Again, we need to get that straightened out. Be happy to help. But you do have to come ask me. So now, can I just go around rotating vectors? Is that fair? Is that legal? Are you allowed to? Well, keep in mind, all I'm interested in is this dot product, F dot n. I just want to rewrite F dot n. And when you rotate a pair of vectors, the magnitudes don't change, and the angle between them doesn't change. That's how you compute a dot product, is with the magnitudes and the angle between them. So rotating, it changes the vector, but it preserves the dot products. So the blue dot product there, because this is a rotation, which is a rigid motion, the dot product is preserved. And therefore, this is equal to that. Everybody on board? It's a slick move. I wish I thought of it. I didn't. Somebody showed me this. Super cool. So now we're actually in really good business. You know, we had this integral that we didn't know what to do with, and now we've rewritten it as this, and we totally know what to do with this because T ds is dx. Right? We've talked about the different ways to write vector line integrals, and in fact, this is just a alternative notation for our good old, regular old vector line integral that we have various theorems that we know about. Okay. And so with that noted, how do we want to compute this integral? And we've got options, and the option I want to pull is to notice that this is a boundary vector line integral, aka a boundary circulation, and we have Green's theorem, which makes for a powerful way to compute that boundary circulation. And it's this right here. It's just a double integral of curl. So a couple of little details that we have to worry about. How do I compute curl? Well, curl, dq dx minus dp dy. Wait a second. Curl of p comma q. is dq dx minus dp. You got to be careful about, what is the what, and don't get stuck on letters of the alphabet. What it really is the x partial of the second coordinate, which isn't q any longer. The second coordinate is p, right? And then minus the y partial of the first coordinate, which is not p any longer. That first coordinate is minus q. So there's curl of my rotated field. And now it really is just a matter of kind of rewriting things. The minuses cancel there. And then we recognize that this is in fact just divergence. I hope you all remember that from way back in chapter 3. This is a formula that I just kind of wrote down and claimed it would show up at some point, and here we are. Divergence is what that turns into. And this gives us what we call the two-dimensional divergence theorem. Right here. Very powerful result. It's kind of a rip-off of Green's theorem, or at least the way I've presented it here. Here you see we have Green's theorem. Green's theorem did the heavy lifting of this argument that we just made, but the punchline is a new theorem that outward-oriented boundary flux can be computed with a double integral of divergence. Really cool argument. All right, example to follow. Any questions before I do that? Everybody see where this came from? Yep.
Wait, can you explain how you go from curl of f perpendicular?
Yeah. So that's right. So let me go back to where we defined, curl in the first place. I wrote down this formula, right? But it's easy to lose track of what's the p and what's the q, right? So the way I like to think about this is the thing you take the x partial of is really the second field coordinate, right? And the thing you take the y partial of, well, it's the first field coordinate. Right? And so that's what I did in writing this down. X partial of the second field coordinate. Now keep in mind, specifically of f perp. Right? We're not interested in f. Right? And then, so minus the y partial of the first field coordinate. Yeah. Okay. Yep.
And so I feel like my question is, we always have to also ensure that our region is on the left, so that's when we rotate.
Now this kind of does that for us, because anytime you have an outward normal, which again is the standard convention, the fact that I'm doing my rotation counterclockwise, right, will always put that resulting tangent vector in the correct direction. It'll always be, if n is outward, 90 degrees counterclockwise will always put the region on my left.
Yeah, and do we always, then the question is, do we always have to just rotate it? If it's like outward, then do we just have to rotate it 90 degrees counterclockwise?
I mean, I don't know what you mean by always. We've already done the argument, right? Yeah. So I mean, this already has that built into it. So so the argument that justifies this only has to do it once, and we already did it. So yeah, right. Okay. So let's see an example. So we've got the unit circle here. Let me draw a picture. Here's the unit circle. And let's see here. It says we want to go outward through the unit circle. Okay, so there's our orientation outward. And we're supposed to compute the flux, it says. Now, wait a minute. We have our theorem. Our theorem is about computing boundary flux. So this formula right here, right, only works if, in fact, I'm interested in boundary flux through a boundary. So this was not phrased as flux through a boundary. The word boundary isn't written anywhere in the statement of this example, right? But is it a boundary? Why, yes, it is. Right? And outward as it should be. So even though it didn't say boundary, it is a boundary, and so we're going to use the boundary flux theorem that we just wrote down. And so with that established, there's our theorem. Double integral divergence. The divergence is easy to compute. We take the x partial of the first coordinate plus the y partial of the second coordinate. And that results in an integral that's pretty doable, right? Our integrand's a constant. You factor it out. All that remains is the area. It's the area of the unit disk, etc. So, victory. But yeah.
I'm sort of confused. Like, what does the problem mean when it says outwards through the unit circle? Like, if it said inwards, like, what would it be?
Yeah. So inward would mean that I've got the unit circle like this. And if it had said inward, then for whatever weird reason, we'd be interested in keeping track of the extent to which the fluid is flowing like this through the circle. Right? And that's natural, right? If this circle is the wall of your city and you're being infiltrated by hordes, right? And you want to keep track of how fast are the hordes coming in, right? That's what you'd want to compute. All right. Cool. All right. Okay, so moving along. Now I presented this as a kind of a tweak of Green's theorem. Remember, Green's theorem right here did all the heavy lifting, right? The bulk. I mean, I really relied on using Green's theorem to turn the boundary question into an interior question. And so all of Green's theorem kind of was essential for this argument to work. But it turns out there's a completely different point of view you can take on this that's just as good, arguably better, depending on how you look at it. Certainly entirely independent of Green's theorem. And it is based on the fact that boundary flux is its own accumulating quantity. Forget about circulation. We don't need circulation. Boundary flux is an accumulating quantity. So I think it's important that I persuade you that boundary flux is an accumulating quantity. So as in all cases, we're going to look one side at a time. I'm going to draw a picture of what boundary flux looks like for each piece, and let's see if they add up the way they're supposed to. So I have that piece and that piece, all oriented outward, as is the convention. Outward, I emphasize, from the thing whose boundary we're talking about. We're talking about D1 at first, so outward from D1 is that way. Okay, now let's look at D2. D2 has a piece of boundary that looks like that, another piece of boundary that looks like that, and outward on those looks like this. And again, I emphasize, as part of the boundary of D2, outward is that way, away from D2, the thing we're looking at the boundary of. Okay, do these add up correctly? I'm concerned about this shared edge here and the fact that it appears twice, and that's not part of the boundary of the whole. I mean, it's just not the boundary of the whole. The whole is this whole lump. The boundary is just the kind of the elliptical curve around the outside. What's up with all this stuff on the inside? That's not part of the boundary. I'm not optimistic at a quick glance, because I've got a bunch of stuff in here that's not supposed to be there. But that same edge appears twice with opposite orientations, which means we're going to get the exact negative value. And so they cancel. And so it's like they aren't even there. Right? So because of the orientation point, those disappear, and conveniently what we're left with is literally exactly the boundary flux of the whole. So as it was supposed to work out, boundary flux is an accumulating quantity. Everybody see that? So I feel it necessary to point out how analogous this argument is to the almost identical argument we made when we were talking about circulation. It's the same thing, just through instead of along, right? That cut edge, the shared common edge, appears twice but with opposite orientations through, as opposed to here, it appears twice, but with opposite orientations along. But really analogous, right? So very cool little observation there. And by the way, that observation is going to keep showing up again and again. Let's see, where are we now? Yeah, here we go. So yeah, accumulating quantity. And whenever you have an accumulating quantity, you can do this same thing, right? So mass accumulates, the whole is the sum of the parts, and we can talk about the associated density. We argued to get Green's theorem that circulation is an accumulating quantity and there is an associated density. And now, well, flux, boundary flux. Just to be more explicit, outward-oriented boundary flux. And by the way, people get tired of saying that over and over again, so I'm just going to say flux, right? Anyway, to be explicit, outward-oriented boundary flux is an accumulating quantity. Whole is the sum of the parts, and on any individual piece, you can talk about the associated density. Right? So I really like showing the strength of the analogy between these various theorems. These theorems here are, go by various different names, but they're really talking about accumulating quantities and treating accumulating quantities the way you can treat accumulating quantities. So I always call these accumulation theorems myself. Sometimes I call them density theorems because, again, density is playing a critical role here. Right? And I think it's super valuable to see how the accumulation is just like with mass. And the role that the densities play is just like with mass. I think there's a lot of satisfaction and good intuition to be had by thinking about them in this way. Real quick cultural point. This term right here, flux density, very common. That's not just me and my own pet point of view. Right? Flux density is super duper common. In fact, when I was in college, taking a bunch of physics classes, y'all are in engineering, I understand, but very similar. I heard this term flux density more than I heard the term divergence. It's in very common use, and I love that because it's so. It's perfect. Right? It's not just a word that sounds like what we're talking about. It's a word that explicitly describes what its role is. Divergence, this thing, its job is to be the thing that I multiply by size to get stuff. Its job is to be a density. And what kind of stuff? Oh, yeah, the stuff is flux. Thus the term flux density. I could not come up with a better term if I tried. I think that's exactly the right way to think about divergence. Right? Okay, now that said, I will confess this term, circulation density, to describe curl, not as common. You won't hear that as much. But I like it just as much. It makes just as much sense. Again, its job, it's the thing that you multiply by size to get stuff. So it is a density in exactly the same way. And again, what kind of density? Well, circulation density. That's what kind of density. It makes exactly the same amount of sense. It's a really great way to think about it. Okay. All right, so in my class, you're going to hear a lot of this. Outside of my class, not so much. Okay. All right. So, new accumulation theorem from last time. New accumulation theorem from today. I'm about to show you a third accumulation theorem. This third accumulation theorem is actually a theorem you've seen before. You've used it many times. You've gotten probably tired of using it. You've used it so much. And betting you've almost certainly never thought of it as an accumulation theorem. But really importantly, it is an accumulation theorem, and that is the fundamental theorem of calculus. Fundamental theorem of calculus is about an accumulating quantity, if you look at it just the right point of view. The accumulating quantity in question is change. Right, f of b minus f of a. That formula for some given function f. That is an accumulating quantity. The whole is the sum of the parts. And I think this is a pretty easy argument to make. If there's some number that you're keeping track of, right, and if you keep track of how much does it change on each little incremental piece, you look at how much it changes as you go along, the total of all those individual changes, of course that's the total change. Right? Does that make sense? Is everybody on board with that? I can draw a little picture here, but if this is A and this is B and this is C, the amount that F changes between here and here, oh, I didn't give myself enough space. Well, okay, whatever. The amount that F changes from there to there, plus the amount that F changes on the second. This amount of change plus that amount of change gives me the total change. Right? Well, of course it does. Okay, so we have an accumulating quantity, and again, once you've established that you have an accumulating quantity, it's all kind of downhill from there. Accumulating quantities have an associated density, and it's going to turn out, and I'm going to give you an argument for this later, but the associated density for change is the derivative. And again, let me circle back on persuading you of that in a few minutes. Okay, so accumulating quantity and the fundamental theorem of calculus. Integral of a derivative is f of b minus f of a, right? That's our old point of view on the fundamental theorem of calculus, is therefore an accumulation theorem. Okay, so why am I showing you this? I'm a big believer in analogies. I think a great way to learn things is to relate it to something you already understand, and then kind of do like this. Okay, with this part I understand. Okay, the analogous thing over here. Okay, so why does this work? Okay, well, so this apparently probably works for similar reasons to why this works. Oh, yeah, because you do the, okay. And then you can kind of make sense using what you understand about what you already have to give you guidance on how to think about what you're trying to understand. Does that make sense? Okay, so I think this is a great example of that, and so we can use what we already understand about the fundamental theorem of calculus, what we already understand about the derivative, as a tool for making sense out of Green's theorem and the two-dimensional divergence theorem, and likewise curl and divergence. All right, now there is a specifically nice thing about the fundamental theorem of calculus, and that is that we can actually see it kind of in action on a graph. And the dimensions are sufficiently low, right? We have one input dimension, one output dimension. We can draw it on a piece of paper, like I have here. Okay, so let's talk about the accumulating quantity in question. The accumulating quantity is change. Right, here's a picture of change. F of b minus f of a. Right? View it as being that increase, as what I've drawn here. So how do we compute that change? Well, it's f of b, so we're going to look at the endpoint b, and then minus f of a, we'll look at the endpoint a. The way we compute change is by looking on the boundary. Okay. Let me go back to the circulation theorem, Green's theorem. How do we compute circulation? Well, we compute circulation on the boundary. Now, I made a big ask of y'all several pages prior. Let's see here. I make a big ask that when you have an accumulating quantity, you can think of it as actually distributed over the interior. And that seems kind of weird in this case, because wait a minute, I'm supposed to think of the circulation that's clearly being computed on the boundary as somehow mysteriously happening in the interior? Come on, right? That's very weird to think of it that way. And the fact that the algebra works out as it does here, not necessarily a huge amount of satisfaction from that. Okay. So how can I persuade you that when something is computed on the boundary, it might actually very naturally be literally happening in the interior and in a way that you can actually see? And this is where the fundamental theorem is super convenient. So let me get back to that. Here, our accumulating quantity of change is computed on the boundary. B and A, right? If you want to compute f of B minus f of A, you only have to look at those boundary points. Is that where change happens? Rhetorical question? Not at all. Right? Change happens here. Right? You can see it happening. There it is. Right? You can watch the graph of the function. The function's not changing along in here at all. Nice and flat along in here. There's no change. Here's where the change happens. You can see the change happening. These are the values of x where the change is happening. Not at B. The change is not happening at B, and the change isn't happening at A. That's just a convenient formula for how to kind of aggregate the total change, I guess. But the change obviously happens in the middle, in the interior. Does that make sense to everybody? Okay, so this is what I'm claiming right now. I can't draw the analogous picture for Green's theorem because the analogous picture, well, gosh, there's a vector field involved, and the vector field has 2 inputs and 2 outputs. It'd be a 4-dimensional picture. We can't draw that. Don't try to visualize that. Right? It's not really on the table. But I argue that in the same way that this accumulating quantity computed on the boundary actually and of course happens in the interior, likewise with circulation and likewise with boundary flux. It's actually happening in the interior. Totally analogous. All right, now next observation, how much? How do I see change density here? And I've made this assertion, this highly suspicious assertion, that the derivative is change density. Weird. Let me try to persuade you of that. Now, I think what you're already probably willing to accept is that if I look at some little interval down here, let's say between there and there, on a little interval like that, if I look at oh, you know what? Let me switch to the pencil. Oh gosh, it'll be a little bit easier to draw. If I look at this little piece of the graph there, the slope of that line is what the derivative is, isn't it? Right? Slope, rise over the run. All right. Well, let's look at the rise and let's look at the run. Let's see the rise. Oh, and I made a bad color choice here. Let me fix that. There we go. What about the rise? The rise is this little bit right here. It's the sort of the vertical side of the little triangle that we're all familiar with from Calc 1. And I'm going to think of that as being representing how much the function is increasing. That's a little piece of change. What we call the rise, when we say rise over the run, the rise is representing some part of the total amount of change that we're computing, the total amount of change that we witness on the boundary. So it's a piece of this accumulating quantity called change. And then, okay, fine, let's look at the run then. What's the run? The run is that distance there. And that, of course, is the size of that little piece of the domain that I'm looking at. So, admittedly weird, sure, right? Admittedly weird, but it actually is completely reasonable to think about the derivative rise over the run as being change per unit size, and change was our accumulating quantity. Quantity per unit size is a density. So I'm going to add this to a list of points of view that I want to encourage y'all to think about when you're thinking about the derivative. Yes, the derivative is a slope. Yes, it's suitably set up and interpreted. It's a velocity. It's a sensitivity if you take an econ class, and various different ways that you can think about the derivative. Add to that list change density, right? And the more you can digest, kind of get comfortable with the idea of the derivative being a change density, the more that's going to help you see the analogy and help you understand curl as being circulation density and divergence as being flux density. So please try to soak those in. Now I'm going to try to draw a little bit of a picture. We'll start with this here. Not sure how much we're going to make on this. So we've got a function here. F of x equals x squared. Function changes. It's not constant, of course. Where's the change happening? Is there more change happening at x equals 1, or is there more change happening at x equals 2? Now, obviously, you could look at the picture. You've got geometric intuition. You could break this down in a million different ways, of course. This is a silly question. You don't need algebra for this. The point, again, is not the answer. The point is the point of view that we're going to take. One way to think about, if you want to know how much of some accumulating quantity, if you want to know how much of an accumulating quantity is happening in one of two different places, is there more here, is there more there? You look at the corresponding density. Density tells you how much of that stuff is happening near a given point. Well, the change density is the derivative. The derivative is an easy formula. You can plug into that easy formula your two different points in question, and you can just literally see which one of these is greater. And apparently the change density is greater here than it is there. More change density means more change is happening near this point. Which again, that tracks with our picture. So this is a nice point of view in the same way that the derivative as change density points to where change is happening. Likewise, curl as circulation density, curl is telling you where the circulation is actually happening, where this overall rotation of the fluid, where is that rotation happening? Curl will tell you, right? And likewise, divergence as flux density. Well, if there's an overall amount of flux density tells you where that flux is actually coming from, where that flux is actually happening, just by, whether it's large or small. And I see now I'm out of time. So we will draw the line right here today. And by the way, just for your own curiosity, the rest of this, page and a half is pretty optional supplemental stuff. I'm going to let y'all take a read on this. If you have any questions, come talk to me. I'm going to declare us done with this section. See y'all later. Have a good one. Yeah. Don't forget about attendance if I didn't already get you.